I'm sorry, is this seat taken?
Yeah, it's all yours.
Is this Biostat 6618?
All the math you love to hate.
Oh, come
You're
on.
in the right
It's
spot.
intro to the Bayes. How hard can it be?
It's
your bread and butter, baby. What's your jam? What's your jam?
Professor's okay.
Greetings, Bio 6618. In this lecture, we're going to have an introduction to Bayesian methods. We'll first have a brief introduction and comparison with some frequentist approaches and ideas and concepts. We'll then introduce MCMC and some diagnostics. We'll then move to Bayesian summaries from the posterior distribution and highlight how they're comparable or similar in certain ways to frequentist summaries we've already learned about most of the semester. And we'll close with a brief example of prior specification. We'll save some specific applications to regression modeling for a future lecture. Let's start by comparing frequentist versus Bayesian statistics. Almost all of the methods we've covered this semester have been rooted in a frequentist approach to statistics. This is based on those long-run probabilities of how probable a dataset is given a null hypothesis. Really, for a refresher of the concepts behind this, refer back to our lectures on p-values and that null hypothesis significance testing or NHST framework from earlier in the semester. However, an important alternative approach is known as Bayesian statistics. This focuses instead on the probability of a hypothesis given a certain data set, so it's turning this idea sort of in reverse. Bayesian approaches are also able to incorporate prior information into our analysis, making different assumptions about our modeling framework, and we'll see have different interpretations for the quantities of interest or different summary statistics we get out. The purpose of this lecture is to give a crash course or brief high-level introduction to Bayesian methods, noting that in many cases this is a full semester class, not just 1 or 2 lectures in the course of our semester. So let's start with an overview of Bayesian methods and some of these ideas we've already seen in a few iterations earlier this semester. For the sake of notation, let's let X be our observed data set, so this would be our outcomes and maybe predictors in a regression framework. And we'll let theta represent our parameter or potentially multiple parameters of interest that we wish to estimate. Now, for example, parameters we might estimate are like the sample mean or the coefficients in a regression model. Now, according to Bayes' theorem, we have this nice little equation we see at the center of the screen here, and I've tried to color code to give a little more of a direct connection since obviously we're just comparing thetas, x's, and these probabilities. Now, what we're really interested in identifying for all of our inference is this red quantity at the left-hand side, that posterior of interest. But thanks to Bayes' theorem, we know we can rewrite this in terms of a likelihood, our blue term here, a prior, where I've just drawn the little star, p of theta, as well as what we call on the bottom here, a normalizing constant. In the next few slides, we're going to define and give a little more detail on each of these components. Let's discuss the likelihood first, or the probability of x given theta. The likelihood is, generally speaking, the joint density function of our observed data to be analyzed. You may see it with some different notation depending on the source or context, such as L of theta or L of theta given x. In our case, though, this is equivalent to our probability of x given theta. Now, in our likelihood function, we're assuming our data is fixed, and we consider theta our parameter or parameters of interest over the whole range of possible parameter values. Now, in our class 6618, we're only assuming cases which are known as independent and identically distributed, or IID data, where we can have a product of the PDFs or that probability density function for some distribution at each observation x sub I. For example, in the context of linear regression, the focus of the latter half of our semester, we see we have something like this, where we have as a generic notation this idea of the product from I equals 1 to n. So for each person, we put into the likelihood their observation for their x sub I given theta. Specifically, we see for regression here, though, it's beta naught plus beta 1 x sub 1 for that ith person's value up to some arbitrary number of coefficients or predictors k. And of course, we have a assumed constant homogeneous variance for our likelihood. Now, one thing to note here as well is that we do use the likelihood in both frequentist and Bayesian statistics, so this isn't something unique or specific to the Bayesian approach. What is unique to the Bayesian approach is this idea of the prior, or p of theta. The prior is, generally speaking, our assumed distribution on parameters which quantifies a belief in the values of the parameters prior to observing our study data. Priors are a unique aspect of those Bayesian analyses. Now, the specification of priors in Bayesian models is one of the challenges, since we often may be concerned about placing priors that may be seen as overly informative. In other words, overpowering our likelihood even if the data does not agree with our prior. Now, this can, generally speaking, be handled with sensitivity analyses and looking at a range of prior specifications. And in fact, we recommend in practice you should evaluate a range of different reasonable priors. Now, you may be wondering, what should I specify for a prior distribution? Well, you can specify any distribution. For linear regression, a common option for our beta coefficients tends to be something like a normal distribution with some mean A and some variance B, where A and B will be selected based on the context and how informative or not you wish your prior to be. And we'll discuss this in a little more detail towards the end of this lecture. The final part of the right-hand side of that Bayes' theorem equation is that normalizing constant, or P of x. This is essentially an integration of across x out of all the parameters theta. Its role in Bayes' theorem is to ensure that any probability function reduces to a probability density function, or PDF, with a total probability of 1, much like our definitions we introduced much earlier in the semester. And we'll see here in a few slides as well that this essentially is proportionalized out of our models when we're talking or discussing these in greater detail. What we see at the top here again is that equation that we're integrating out over theta, those values for the probability of x. Now finally, the quantity that's probably of most interest for us for inference is the posterior, or the probability of theta given our data x. Now, this posterior is ultimately going to be used to express the uncertainty in our parameter or parameters if estimating multiple, after accounting for both our observed data and incorporating the priors we'll specify in our models. Now, it is worth noting that there are some simpler contexts where there are what are known as conjugate priors that result in a closed form posterior distribution. An example of this is if you have a, let's say, binary outcome or a binomial likelihood, and you place a beta prior on that probability p, we have what's known as a beta binomial model, and that's a closed form solution with a known variance, mean, and so forth. Likewise, if we have a continuous outcome, let's say a normal likelihood where we assume known variance and we place a normal prior on mu, we actually have this normal-normal conjugate distribution, and so our posterior also is normal. The advantage here for these simpler problems where we do have conjugacy is that we can have closed form solutions and do exact calculations. However, in most contexts, we're actually going to see that we need to use numerical integration to approximate the posterior distribution. This is achieved through a process known as Markov chain Monte Carlo, or MCMC methods, which we'll also detail in a few minutes. As alluded to just a second ago, the Bayesian posterior and that normalizing constant have this idea of something being proportional to, or this funky little sort of fish or almost alpha-like symbol. What we see here is that we write that, strictly speaking, according to Bayes' theorem, we have that the posterior is equal to the quantity here, that probability of x given theta times the probability of theta divided by that normalizing constant, the probability of x. Oftentimes, though, we'll simplify this by using this proportional to symbol, or that, again, kind of fish-like alpha symbol, to just represent it as the likelihood times the prior. This is really just here as an FYI and to help you be aware as you're looking at other examples or resources that you may actually see the P of x left off entirely in some of those examples. Now, in this lecture, we're not going to work with too many data examples, but I do think it's helpful to introduce this figure from the website with the web address below as a source to kind of illustrate the general idea of what's taking place here. And so conceptually speaking, we have, to start off, some idea of a prior distribution or a prior belief before seeing the data. So in this figure here would be this prior P of theta at the left-hand side of the figure. We see here also that it has some variance or variability with that noise information as well. Now, what we actually observe by collecting data for the study is that likelihood function. And again, a lot of what we do in frequentist statistics is based on just that observed data alone. Now, with the Bayesian approach, that we try to average or smooth over those two distributions, and in this more extreme case, we see that together they then result in this posterior distribution in the middle. It represents, again, a smoothing or averaging between that prior belief of, let's say, what looks to be a smaller value and the observed likelihood of having a higher value from the data. Now, this is a bit of an extreme case because we might raise questions about the prior having none of its visible sort of density or sample space overlapping with the likelihood, but it does conceptually illustrate this idea that we can incorporate prior beliefs or information into the likelihood and then average over them to get this posterior, which ultimately, again, we'll use for inference. And we'll discuss how in a few minutes. But before doing that, let's introduce the idea of that numerical integration through MCMC and some diagnostics to evaluate how well we've done. As we noted before, the posterior is often not known or available in the closed form, and this is especially true as we get to more and more complicated models. Now, fortunately, we have this idea of Markov chain Monte Carlo or MCMC methods to simulate samples from the posterior distribution, which we can ultimately then use for inference. Now, the point again of this lecture is an overview, and we're not going to get into much of the specifics, if any, but it's worth noting there are tons of different MCMC algorithms out there that have been proposed. These include some of the more commonly maybe encountered one in intro Bayesian classes like Gibbs sampling and Metropolis Hastings samplers. We'll see also examples of some of the software using no U-turn samplers or NUTS. There's also reversible jump samplers. And in fact, if you just want to kind of play around and look over at different types of MCMC samplers, I encourage you to visit this link here, where they walk through, again, both some of the algorithmic approaches and some of the concepts or pros and cons of the different samplings, with over 40 different ones outlined and for use in R. Now, in general, what we can really think of an MCMC sampler for the depth we're going into for our class to be used as is a recipe, how we can explore the sample space and approximate that posterior distribution through this idea of numerical integration. Now, it is worth noting we can custom code our own MCMC in R or other software as well, but we can also leverage existing software and packages to implement our models. Now, we're going to, of course, focus primarily on R, and we can note, kind of starting off here at the top or middle two paragraphs, there are two older Bayesian languages with R interfaces, which are known as bugs and jags. They are based on the Gibbs samplers. However, they often involve creating your own models and syntax and kind of piping in between the Bayesian language and the R interface, and can be a little clunky these days, but they are very efficient and useful in many cases. What we'll primarily focus on is a newer approach based on a Hamiltonian Markov chain, which is known as the Stan language. There are two popular sets of packages in R, RStan with RStanArm as another package version, as well as BRMS or Bayesian regression modeling strategies, that both help to implement Stan models using standard GLM syntax. You can also, if you are familiar with or do some research into Stan syntax, define your models that way as well. But one of the advantages here, I think, is that it's going to leverage a lot of the familiarity we already have throughout the semester to apply these Bayesian models for linear regression without having to learn a bunch of new coding strategies, given the focus of our class. It is worth highlighting, though, that SAS has various implementations of Bayesian approaches. One is proc MCMC, another is proc GenMod, and Stata as well as a pretty easy implementation of certain Bayesian models for different types of inference approaches. Now, let's discuss some general MCMC output ideas and terminology. The output from your MCMC algorithm after you've run your software will generally be in the form of a rectangular data set, where you will have a column for what we call a chain, or each chain you run, and a row for each iteration. Now, chains are essentially separate instances of your MCMC algorithm, often with different initial or starting values, that help to provide more exploration of the sample space to avoid or see if there are potential for local minimum or maximums that you might arrive at. The idea for this is that if you run multiple chains, you have a better chance of exploring that sample space or identifying if there are the potentials for these non-sort of true estimate areas to arrive at. Now, within each chain, you also have what's known as a burn-in period, where you discard the first, we'll say, n sub burn-in iterations of each chain to provide time for convergence. And again, that's because as your algorithm is starting up, it'll be meandering through your sample space. And we'll see some graphical examples of this in a few slides. But it does take a little bit of time for it to actually identify the general space that it thinks is the appropriate sample space of the parameters of interest. It's worth highlighting that each software and package does have its own defaults for the number of chains, iterations, and burn-in period, and so you may have to play around with this in practice. And generally speaking, I think multiple chains can be helpful, again, to avoid the chance of arriving at a local min or maximum that you can't necessarily escape from with just one chain, or know that you're stuck there. One of the things, though, about MCMC, because this is an approximation to estimate our posterior distribution, we'll want to evaluate how well we think our model and sampler is done, or if changes might be needed. For example, maybe we need to adjust for a longer burn-in period, we need to specify different models, or look at different approaches. While there are tons of diagnostic strategies out there, we're going to focus on just a few in today's lecture that we see listed here, and we'll walk through them in the following slides. We'll start with the idea of trace plots. These are plots that show your posterior estimates for each iteration across all of your chains, or one single chain if you only run one. Generally speaking, your value of the parameters on the y-axis, and so in the example below here, we can see that we have a label for beta 0, or the intercept of a regression model. Now, if your convergence is achieved, it should generally look like random noise, versus if you have some sort of defined pattern that might suggest that there's something questionable in your model, or other things need to be adjusted or revisited. We see below examples from SAS's proc MCMC with a burden of 1,000 iterations already removed for estimating that intercept in the regression model. Now, we can highlight a few things here. First, looking at our iterations, we see that the total number of iterations is 10,000, but we do see at the very beginning here of both figures, we actually start at essentially 1,001, because we've gotten rid of or removed the first 1,000 iterations for a burn-in. What we notice on the left-hand side is that we have an example of good diagnostics, or a good trace plot for a parameter we're estimating. We essentially see that it looks like just a noisy sort of squiggle of lines jumping around what appears to be about a value of upper 80s, maybe 90 for beta 0 in this data example. This is in contrast to our figure on the right-hand side for beta 0. It shows an example of a bad diagnostic plot. In this case, we see that there's a clear pattern where it doesn't really explore the area very well over the entire span of our iterations, and it never really seems to find that random noise sort of area. Here what we can note is that we probably have some either issue with the model or the data at hand that makes it challenging to estimate. In some cases, we may also identify, let's say hypothetically, that we got to the top here and we actually started to see what I'm trying to draw right now is just a little pattern at the top. It could be that if we saw something like this instead, where eventually it achieves sort of a steady state, then maybe we just need to increase the burn-in. But again, this gives us a good idea of the general spread of our data or parameter estimate just across the range of our various iterations from our MCMC chain or chains, and also some ideas if we've done fairly well or not with our estimation. Another type of plot we may be interested in looking at is an autocorrelation plot. It essentially summarizes the pairwise correlation between iterations and different lags between those iterations. So for example, if we just look at the right-hand side here, we see the x-axis is labeled lag, and we can note that as you get farther apart from, let's say, the same iteration where there's a 1.0 correlation, a perfect positive linear correlation, we can imagine as you increase to an iteration that's 5, 10, or further away, we would hope to see less and less correlation. And that's essentially the idea here, that a well-functioning algorithm should have a fairly steep decline as lag increases, with this pattern suggesting samples are likely to be random draws from that posterior distribution, and our simulation is adequately sampled to support of that parameter. Now, from proc MCMC and SAS again, we see this example at the top where we have this nice, again, steep drop of the autocorrelation, versus the bottom figure has a much less steep drop, which may suggest that there is some high level of correlation and we may need to evaluate other ways to improve the efficiency of our algorithm. Another plot that I think is of great interest and use in Bayesian analyses is this idea of density or histogram plots. Now these are essentially visualizations of the posterior distribution as either a histogram or a density plot from your posterior chains or your data. Typically we're looking for a fairly smooth shape with a single mode, But we also might identify that there are bimodal or unusual patterns that could either indicate lack of convergence or the need for a more sophisticated model. Again, it's not a one-stop shop to say that the figure necessarily at the bottom has guaranteed worse convergence, just that we might actually be missing something in the model that actually isn't accounting appropriately for the fact we have a bimodal nature that seems to appear in this density plot. Versus the top figure has a fairly nice unimodal normal-ish looking density in this case. Again, these both represent beta 0 from a regression model, and we know from our regression theory that we expect these to be theoretically approximately normally distributed. One advantage of Bayesian models, though, is this chance to actually visualize your data and its specific distribution without having necessarily a perfectly smooth theoretical fit based on our assumptions. It helps us to evaluate the model assumptions, but also to get a better idea of what sort of the data looks like in our posterior estimation. Now, in addition to those plots to visualize convergence or other potential issues, there are other approaches to numerically summarize performance, and these can also differ by software as what is by default outputted or can be calculated. Just two common ones that you might encounter. One is the Geweke diagnostic. It compares values in the early part of the Markov chain to latter values, and it will implement a two-sided test with a large absolute z-score indicating rejection of convergence, and essentially gives you a way of looking at a quantified z-score to identify if something seems amiss. On the other hand, we also have the r-hat statistic, and this is a potential scale reduction factor proposed by Gelman and Rubin. This will estimate convergence based on variance of estimated parameters between your chains and variance within a chain. One note here is that you obviously need multiple chains to estimate this parameter. Generally speaking, we want values near 1, where some rules of thumb suggest as low as 1.01 or smaller, or even maybe a little more liberal, 1.05 or smaller as being adequate. If you have higher values, it does suggest that you likely have some issues with convergence, which in a circular fashion you will probably catch or notice in your visual diagnostics as well. So now that we've discussed MCMC and other ways to do the posterior very generally and briefly, let's look at ways we can summarize different Bayesian quantities and compare them to frequentist analogs from the posterior distribution. The first thing we're probably interested in getting from our posterior chains or distribution is some point estimate. Now, since our posterior distribution isn't a single value, but in fact, hence the name, a distribution with varying densities over a range of possible parameter values, we have to figure out how we want to summarize the point estimate. Now, in practice, we'll often use one of the measures of central tendency we've covered in the course. So for example, you might take the mean of your posterior distribution. One caveat to this is that it can still, being a mean, be affected by outliers or skewed posterior distributions. You might take the median of your posterior distribution, looking at the value that's smack dab in the middle, or calculate the mode of a posterior distribution, which may not make as much sense if you have a continuous outcome or continuous parameter. Now, these can all be estimated either from the conjugate distribution, if we're lucky enough to have something with a closed form posterior, because we actually know, let's say that it's a normal distribution and therefore it has mean mu, standard deviation sigma. Or if we either don't want to make that assumption of knowing a conjugate distribution, or we just want to fit an MCMC numerical integration approximation approach, we can also pool together all of our posterior chains if we have multiple, and after we discard those burn-in periods, we can then estimate the mean from the pooled chains, or the median, or the mode. Now, the choice of mean, median, or mode likely will depend on the shape of the posterior distribution, the quantity of interest. Defaults also differ by software, so you may find some that provide the median of the posterior as its default and others as the mean. So you should also check what summary is being used in your chosen software. Once we have a point estimate, though, we may also be interested in describing the posterior probability. Now, from our posterior distribution, this is actually pretty easy to estimate because we actually have, again, a distribution in a range of values that we can derive a probability from. And this can test any given hypothesis of interest. This could either be calculated directly from your conjugate distribution. So for example, that beta binomial model, if you have a binomial likelihood and a beta prior on that probability of an event, or we can approximate it from that MCMC posterior distribution by pooling our chains together. Now, relevant to the frequentist approach, this is often thought of as analogous to the frequentist p-value. However, where the p-value has a very nuanced and difficult interpretation, in other words, the probability of observing something as or more extreme under the null hypothesis, A posterior probability has a very straightforward interpretation and is a common misinterpretation of what the p-value or what people think the p-value is. In other words, it's the probability of the hypothesis we're testing. Literally that straightforward. For example, if we had a posterior probability of the mean being greater than 0 equal to this p of theta greater than 0 as 0.89, we would simply interpret this as the probability the mean is greater than 0 is 89%. And we can also estimate this to change it to any other value, mu greater than 0.5, then 7, less than 0.2, whatever we're really interested in, because we now have a distribution we can do all these calculations from. We may also be interested in trying to get some estimate of the variability of our estimators or the distribution, and this comes in the form of what are known as credible intervals. So from the posterior distribution, we can estimate the credible interval, commonly denoted CRI, to help distinguish it from the frequentist confidence interval, which is often denoted CI. Now again, this is often thought of as analogous to the frequentist confidence interval, but once again, I think the interpretation is more straightforward for the most part. The confidence interval has that kind of strange, we're 95% confident that whereas the credible interval is more straightforward in that there's a 95% probability that theta, our true value of our parameter or parameters, falls within our estimated intervals. One caveat, though, or challenge is unlike confidence intervals, credible intervals are not unique on a single posterior distribution, and different assumptions exist for how you calculate the interval. Might think of this as similar to some of the choices we had for bootstrap confidence intervals by estimating it either just from the bootstrap distribution alone or making some normal approximations. Now, I've outlined 3 strategies here, and we'll see a couple of different ones potentially illustrated in practice. But 2 of the common ones at the very top are the highest posterior density or HPD interval and the equal-tailed interval. The HPD identifies the narrowest possible interval within your posterior, and this will always include your mode. It is possible if you have a very strange posterior distribution that this could exclude something like, let's say, the mean or median, which might make it a little wonky for that to be your point estimate summary. An equal-tailed interval, on the other hand, is very similar to the idea of a bootstrapped percentile interval, where we choose the interval where the probability of being below and above the interval is equal. This will always include your median as an estimator, and has equal length tails, even if it isn't necessarily the narrowest possible interval. There's also the idea that we could do a mean-centered interval, so we essentially center it at the mean, let's say, of our distribution, and maybe we take plus or minus some value or somehow construct an interval with that mean at the center to keep some of those identities or ideas that we might think of as common or appreciative in the confidence interval in a frequentist sense. Again, in practice, we can choose any of these, and it might just depend on our setting or preference for what we're working on. The final quantity of interest to then describe in greater detail is the idea of prior specification. And this is one of those tricky challenges in Bayesian statistics. So in this final section, we're just going to compare some different priors on a simulated data set to estimate the posterior mean for a one sample data set using brms and R. We'll walk through an example interpreting outbound diagnostics in a separate lecture for an actual regression application. For our sake, though, we'll simulate 20 observations from a normal distribution with mean of 10 and a standard deviation of 2.5. We see down below we're in the ballpark approximately, with the mean in this case being 8.6 and the standard deviation being 3.1. Now, we're just going to, for today or this lecture, compare different performances of different priors. And many times you might encounter as you're kind of Googling or searching for different information about priors, descriptors like a vague prior, a non-informative prior, an informative prior, or so forth. Generally speaking, these are not well-defined terms and can really depend on the eye of the beholder. Something that one thinks is vague or non-informative, another person in a different context may find to be very informative. Or we may mistakenly think something is non-informative when in fact it is somewhat informative. So it is worth just being aware that you'll see these terms thrown around, and they can be nice qualitative descriptors, but they don't have a firm definition and can vary. Now, for our problem, we're going to implement a linear regression model with only an intercept, so essentially estimating the group mean using brms. And we're going to compare 6 different priors. We're going to look at one which I would think of as the most quote-unquote vague. We're going to center our intercept or mean value at 0 with a standard deviation of 1,000. Remember, we simulated 20 observations from a mean of 10 and a standard deviation of 2.5. So this prior is pretty general and covers a wide range of our possible values. We'll then look at something that would be considered more informative, a number 2, a normal 0, 1, because now the standard deviation is quite small. We'll then, in options 3 and 4, look at the same idea, but again, maybe we have a prior belief that the mean should be 10, so we'll look at what happens to our posterior distributions and densities if we center those at 10 instead. And then we'll finally end with 2 different distributions that we're just assuming are uniform, either over a -50 to +50 range, which in our case we think should cover all of our data since it's, again, 20 observations from a mean 10, standard deviation 2.5 normal distribution. We probably don't expect anything to be as small as -50 or as large as 50 without a very rare event. We'll then also show that you could fit a very informative prior, number 6, which actually excludes our value or simulate mean of 10 to show what will happen. Now again, we'll walk through this in much more detail in a later lecture, but it's just worth noting here in BRMS that we have a very similar syntax. First of all, this very top row of our code for mod 1 and mod 5 of the syntax for GLM. We have our outcome y tilde 1 for our data set, which we call DAT. Now within here we're going to specify our priors as either normal or our family of uniform priors, and you can see the specific syntax here as well. And of course, as always, we'll set our seeds for reproducibility in case you want to try this at home or try to recreate these results or recreate your own results in the future. Now let's assume we turned our analysis crank and we ran all of our BRMS models, and we wish to summarize a couple quantities here. We have a panel figure showing in each one of the panels a different prior, and we have the density estimated either from the density function or kernel densities in R, or plotting our prior distribution from that specific smoothed value we have assumed. So just as an example, let's start in the top left. We can note that the black solid line here is our actual data density estimated with the smooth kernel, versus the blue dotted line is the theoretical normal distributed density with mean 10 and standard deviation 2.5. We include these on each figure just to help us see the idea of the likelihood or the observed data, and also theoretically what we should be simulating from. Just to note that with only 20 observations, we don't have a precisely normal distribution, but it's not, completely out of whack necessarily. We can then note that the gray lines in each figure represent the prior distribution, which in many cases like here looks to be essentially a flat line because the density is distributed across so many values with that standard deviation of 1000 that it basically is hard to see without zooming into very, very, very small densities. Then ultimately what we're interested in comparing is that blue posterior distribution, and we can compare, just quickly glancing across all these different 6 panels, that it does shift quite a bit depending on our assumptions of each of the models. Now, we can note that in the case with our large variances, so in the top left and the top right figure, or in the case of a uniform with a wide range of possible values, all of these do have similar-ish posterior distributions, at least locations of them. We can note that in the top left with a mean of 0, it looks slightly smoother. In the top right, there's a ever so subtle little blip at the top of our distribution of the posterior. And even then, again, for the uniform one, there's a subtle little blip as well there. However, these look somewhat similar, suggesting there's a little bit of robustness if we change the mean parameter, or let's say we used a fairly large or wide uniform distribution. Now, these results don't necessarily hold if we have something that is, like in the middle top panel, a fairly informative normal 0, 1 prior, because what we see now is that actually even though our black likelihoods or observed densities are over there and our gray priors are here, there's really not a lot of overlap for the data points kind of right in the lower part of the figure there. And in fact, our posterior is kind of like that graphic we had earlier, which is this kind of comically smooth value between the two, even though the prior and the likelihood of the observed data don't really mesh well. Now, if we focus on the different case of having a normal 10 standard deviation of 1, this is not as badly performing, mostly because we, in this case, knew we simulated data from a mean of 10, even though it was 8 point something. We can note here that, the posterior is actually still fairly close to or similar with the prior and the likelihood to get an estimate that might be pretty close or analogous or with some of these other priors. Now, The hard thing with Bayesian methods, especially if we aren't careful, is in the bottom right figure where we see the uniform negative 5, 5 leads to very strange behavior because we've essentially said that the mean has to be between negative 5 and 5, and it is impossible with a uniform distribution to fall outside that range. So what we see essentially here is that we have this weird spike in our density here from the mass because it's really trying to match or mesh with the likelihood of our data, but we've made this artificial constraint that it really cannot pass 5. So it leads to some strange behavior that we see here in the density plot that might lead us to think that we should revisit our model in some ways. Let's close with a brief summary now. The point of this lecture was to highlight that Bayesian methods have a different approach to inference than frequentist methods, and to introduce the concepts and terminology that we'll be applying in practice to some example lectures later on with multiple linear regression. We did see that the choice of prior specification can be challenging, but it does give great flexibility in our modeling to be able in the Bayesian approach to incorporate these prior beliefs or information to specify a prior. And remember, in practice, we actually should look at a range of priors for any analysis to check the sensitivity and robustness of our posterior inference to changing prior specifications for what we think are reasonable priors. Bayesian quantities like the posterior probability or credible intervals do have intuitive estimates and interpretations in comparisons to frequentist quantities like p-values and confidence intervals. And as I mentioned, we will explore more specifically in later lectures the use of Bayesian methods to actually apply to multiple linear regression and to apply some of these concepts, diagnostics, and interpretations. But with that, I hope you enjoyed learning a bit about the basics of Bayes and look forward to actually applying it to regression in our next lecture.